Please, welcome to the stage, co-founder and CEO, AnyScale, Robert Nishihar.
Welcome to Ray Summit. Quick show of hands. Who took an Uber here? Who chatted with Chachi Beauty recently? Raise your hand if you used Spotify or Netflix or TikTok recently. Or perhaps you ordered food on Instacart or DoorDash or Uber Eats or used any of these products. Just about everybody. You all have interacted with models built using Ray. Thanks to the work that this community has done, that we've done together, for businesses scaling AI, Ray is everywhere. And the impact has been staggering. Instacart uses AI across the board for fulfillment, for ads, personalization. They now train 12 times faster and on up to 100 times more data. Pinterest has some of the world's largest computer vision data sets. They cut costs by 40% and increased developer productivity, speeding up developer iterations by 6 times. Amazon processes exabytes of data with Ray. They reduced latency by 10 times, they increased scale by 10 times, and they, most importantly, cut costs by 10 times. I find these numbers just extraordinary. But perhaps, thank you. Perhaps it'll come as a surprise that just 1 year ago, almost none of these success stories existed. In fact, even 6 months ago, almost none of these success stories existed. The Ray community has exploded over the past 6 months, in large part because AI has changed so rapidly. When we had this conference, our first in-person Ray Summit, just 1 year ago, there was no ChatGPT. And there were definitely no llama models. In that time, AI has become far more capable. And as the capabilities have grown, the challenges have also grown as well. So what are these challenges? Well, we all know the models are larger. The computational demands are more demanding. We used to actually get this question all the time. People would ask, isn't scale something that only the biggest companies like Google need to think about? Well, we don't get that question anymore. As scale has become a fact of life, cost is now top of mind for nearly everyone that we speak with. But beyond the scale and cost challenges, the pace of AI itself has become a challenge. We've talked to so many businesses who've been doing AI for years, who've invested heavily in AI infrastructure. And yet many of these businesses have found themselves lacking the capabilities to fully take advantage of LLMs and generative AI. And as a consequence, they're starting to see their competitors catch up, or new competitors emerge. Succeeding with AI today is essential. But just as important is preparing ourselves for all of the challenges and the changing requirements coming down the road. AI is not done changing, and the infrastructure challenges are going to continue to grow. Now, fortunately for many of us here, these are precisely the challenges that Ray was built for. Scale is our bread and butter. The largest models out there, like ChatGPT, were built with Ray. Cost efficiency is baked into Ray at every level, from the way we handle auto-scaling, to the way we separate CPU compute and GPU compute, to the fault tolerance capabilities that allow Ray to run on spot instances, to the way we pipeline data ingest and training and inference, to the low-level model and GPU optimizations. Cost efficiency is baked in at every level. But another reason, when we ask businesses and teams, why did they adopt Ray? We hear scale a lot. We hear cost a lot. But we also hear another reason. Teams adopt Ray because it is strategic. AI is not done changing, and the challenges are continuing to grow. And we've seen many shifts before. We've moved from classical machine learning to deep learning, and then from deep learning to LLMs. And today we're all using LLMs, but soon we'll all be using multimodal models, working not just with text data, but also video and image data. It's going to become far more data intensive. On the hardware front, the variety of accelerators that we need to support will grow. On the application front, applications are becoming far more complex. Techniques like model routing are becoming essential as many models work together to power individual applications. Ray is designed to be future-proof, to give teams the flexibility to adapt to all the changing infrastructure requirements coming down the road, and to stay at the forefront of all the advances in the AI and the open source community. We always talk about the rapid pace of progress in AI, but what good is the rapid pace of progress in AI if your team isn't fully prepared to take advantage of it? So some of you may be wondering, what are we working on here at Anyscale? Our first product is the AnyScale Platform. This is our managed Ray offering. We recently announced AnyScale Endpoints in preview. This is an LLM API, an LLM inference API, like the OpenAI API, but for open models like Llama 2. These two products mimic different stages of the generative AI adoption lifecycle. From talking with many of you, we've seen that businesses tend to adopt generative AI in two phases. At the outset, you're not looking to curate a large data set and train a model. Instead, what matters at this stage, you want to start with an API product like AnyScale Endpoints, integrate it directly into their product and features that you're shipping. What matters at this stage is rapid iteration, shipping your product, and actually validating that the product makes sense. That's why we built AnyScale Endpoints. Now, once it's proven out, then the story changes. Then it's about making it real. At that point, what matters is scale, reducing costs, reducing latency, improving quality, extending and expanding the application. So here's a little illustration showing what it looks like to use AnyScale Endpoints. Here we're passing in a query. It's an API product. The query is showing CodeLlama a code snippet in Python and asking it for help debugging the code. Okay, I'm not actually showing the full code snippet. But amazingly, CodeLlama actually correctly diagnoses the bug in my code and tells me how to fix it. I think it's pretty impressive. CodeLlama is a great model. But CodeLlama is just one of many models. We support all the most popular open models. And helping me debug is just one of many possible use cases. But hopefully this gives you a taste. Now, since we launched it in preview just 1 month ago, it's been exciting to see the first production applications roll out built with endpoints. One of our customers builds a browser extension, an AI-powered browser extension used by millions of people. They use AnyScale Endpoints to achieve a 5 to 8x cost reduction. Another company builds an AI character chatbot. They use AnyScale Endpoints not just to reduce costs, but also to ship new services in hours instead of weeks. And AnyScale Endpoints is used to build products. It's not used in isolation. And to support that, we integrate with the rest of the AI ecosystem, tools like LangChain, Weights and Biases, Llama Index, Arise, and many others. Some of you may be wondering, aren't there lots of LLM APIs? What's different about this one? Where we go deep is on cost efficiency. Optimizing cost for LLM inference touches every layer of the stack. It's a very holistic problem. To illustrate that, It requires low-level GPU and model optimizations, techniques like page detention, tensor and pipeline parallelism, taking advantage of techniques like continuous batching, rapid auto-scaling of model replicas to handle variable load, and thinking about how to take advantage of the most cost-efficient and cheapest hardware and GPUs across different regions or maybe even different clouds. This is a deep, deep technical challenge. And our goal is to go deep at every layer to squeeze out the most performance, taking advantage of all the optimizations that we've built over the past couple of years, along with all of the latest advances from the open source community. And we take all of that work and all of these layers and put it behind an API and offer that for just $1 per million tokens. That is the price point for the 70 billion parameter llama model, and that is the lowest price point on the market. But what if you want to go further? Can you reduce costs even more? Well, maybe to state the obvious, one of the important directions to go in for cost reduction is to use smaller models. The challenge there is that smaller models don't work as well. So what do you do about that? Well, fine-tuning is a technique that adapts models to improve their quality on specific problems by doing a little bit extra training. So fine-tuning can actually it can make smaller models viable. And by enabling us to use smaller models instead of larger general purpose models, fine-tuning can play a huge role in cost reduction. So because of that, I'm thrilled to announce that today we are releasing fine-tuning support in Anyscale Endpoints. This is now part of the API, and you can try it out today. To give you a sense of why fine-tuning is important, I want to share one result from a study we did. So here we compared a few different LLMs on a specific problem. We actually did many problems, but the specific problem here is SQL query generation. So taking an English statement and translating that into a SQL query. Out of the box, the smallest llama model, the 7 billion parameter llama model, doesn't work. Okay? This is unusable. On the other hand, GPT-4 actually does quite well out of the box with 78% accuracy. Okay, so the small llama model doesn't work. GPT-4 works quite well. There's nothing surprising here. What is surprising is that when we fine-tune the small llama model, it actually achieved 86% accuracy, outperforming GPT-4. So we are comparing a small, specialized model with the most advanced general purpose model out there, and we're seeing superior task-specific performance at 1/300th of the cost. So we are all going to be doing fine-tuning. So to give you a taste of what it feels like to use this API and what you can achieve with it, I'd like to invite Robin from our product management team and Amir from our engineering team to the stage to give you a demo. Please welcome Robin and Amir.
Thanks, Robert. With the Anyscale endpoints, you could host and scale your open source large language models that can perform as well as closed source models for specific applications. Today, we are hosting Llama family of models, and these models are powerful enough to replace closed source model for specific applications. These applications are like summarization and entity extraction. Let me show you a quick demo of this. Last week, NVIDIA released TensorRT libraries for LLM. They mentioned Anyscale as one of the partnering companies. What I'm going to show you right now is I'm going to ask both GPT 3.5 and Llama 70 hosted on Anyscale endpoints to summarize this article and give me the names of the partnering companies in this article. Let's look at this in action. First, I'm going to go and ask GPT 3.5 to summarize this article for me. Well, it does a reasonably good job at being able to summarize this. Now let's ask Llama 70 model running on Anyscale endpoints. By the way, in both the cases, There's OpenAI SDK being used in both their programs. That's because Anyscale Endpoints API is OpenAI compatible. You see both of these things, both of these models are able to perform fairly well in summarization and entity extraction. But Anyscale Endpoints is able to do the same exact job for 40% lower cost. That's amazing. Now, let's push this model a little bit further. How about we ask it to do something that it hasn't done before? How about we ask it to convert a natural language into a SQL query? What I'm going to do is I'm going to ask Llama 70, hosted on Anyscale Endpoints. I'm going to give it a public database schema, let's say the names of the presidents and the year that they were president, and ask it to generate a SQL query which tells me precisely who was president back in 1990. Now, let me just ask this. Tell me who exactly was the president in 1990 and generate a SQL query. Well, you can see it doesn't do a very good job at this. And this is exactly what we have seen so far. Large models, both open source and closed source, are not powerful enough to be able to do this domain-specific tasks. And that's exactly why I've built Anyscale Endpoints Fine-Tuning API. To do a quick demo, Amir's going to walk you through it. Amir?
Cool. Thanks, Robin. I'm very excited to show you how fine-tuning works on Anyscale Endpoints. Right now, I will be taking a 7B model, which is much smaller than the 2 models Robin showed you earlier. I'm going to fine-tune it, and I'm going to send it this same exact query, and you're going to see that it will handle this task correctly, while being 300 times less expensive than GPT-4. Let's take a look. This is my fine-tuning script. Notice how short it is, and notice that it uses the OpenAI SDK, because our Anyscale Endpoints is compatible with the OpenAI SDK. All I have to do is run this script, and this will get my job scheduled. Anyscale Endpoints will take care of running my fine-tuning job, getting the GPUs, figuring out all the hyperparameters, etc. Once my fine-tuning job is finished, I will get an email notification, and my model will become available for serving. And then I can use the same script used earlier by Robin to query my model. Let's try that. Now I will be pasting the same exact query that Robin used earlier, but now on my 7B model. Notice how clean and accurate the response is. It just gave me the exact query that I would need that would give me the response correctly. I want to also remind you that this model is 300 times less expensive than GPT-4. I'm very excited to see what you guys will be building on top of Anyscale Endpoints. Now back to Robert.
Thank you, Robin and Amir. I'm so excited for you all to try out this API. There are a lot of things you can build with it. But sometimes you do need more than just an API. I may need more privacy. For example, I may have highly sensitive customer data, and that data and my models simply can't leave my control. Or perhaps I need more customizability. I want to deploy different models, adapt those models, or modify the logic surrounding those models and surrounding the operation of those models. Or perhaps I need other forms of control. I want an SLA. I want to use dedicated compute. I want to choose the hardware myself so that I can trade off cost and latency considerations. All of these requirements go beyond a typical API product. So to make this possible, today I'm very, very excited to be releasing Anyscale Private Endpoints. This makes it possible to deploy the entire back end, including all the LLMs, in your cloud account, private for your business, and to customize it to your heart's content. I'm incredibly excited for people to try this out. There are many LLM APIs out there, but I don't think there's anything else like this. You get the same familiar API, but with the customizability and control of your private infrastructure. To show you what it feels like to run the entire backend yourself with Anyscale private endpoints, I'd now like to invite Praveen from our engineering team and Matt from our product management team to join me on the stage to give you a demo. Please welcome Matt and Praveen.
Thank you, Robert. As Robert mentioned, sometimes we need more. One of the things I do in my role at Anyscale is understand how customers use our product. This means writing a lot of complex queries on our production database systems, and this could take a lot of time. Let me see if Llama can help me here. Now, I'm going to start with a very simple example. I want the model to give me a query which will tell which customer used a particular product most in the last month. Now, before coming on the stage, I've played around with the query a bit, and what I've realized is I need to give it some context. The context here happens to be the database schema that we are running on. This could be a problem. My security and privacy team may not be very happy with me transferring a database schema of production system outside my org boundaries. You can imagine more use cases like these. What if you're summarizing logs which have sensitive information? This is where Anyscale private endpoints can help. I was able to take everything that Robin and Amit have shown previously, deployed in my own cloud as a private endpoint. Now, in this script, with one line of change, as you can see in the screen, I was able to point this query to run it against my private endpoint. I'll still get all the benefits of the public endpoints, but hopefully keep my security and privacy team happy. Let's see if we can run this query. As you can see, it generates a valid SQL query for me. But we can do more. There is a bug in this query which is not obvious. The group by clause happens to be wrong. Now, I know I can fix it by fine-tuning this against the production queries that I've run in the past and get the results that I want. But that means exposing more of my schema outside my org. Private endpoints helps us out here as well. With the same line of change that I've shown you earlier, I can point the fine-tuning job to run against my private endpoint. I can still get all the benefits, optimizations that Amir and Robin have shown while running this on my cloud, hopefully keeping my security and privacy team happy. You can do that as well. Let me invite Matt to show you how to create and manage your endpoints.
Thank you. Let me show you how Anyscale private endpoints made it possible for Praveen to run his LLM application with more privacy, control, and customizability. Now, the first thing we wanted to do with private endpoints was make it super simple to deploy. With the simple click of a button from the AnyScale Platform homepage, Praveen was able to deploy the Anyscale Endpoint solution privately in his own cloud. Let that sink in for a moment. The performance, reliability, and scalability of the Anyscale hosted endpoint solution, plus the privacy of his own cloud, packaged together in a single button. But there's more to it than that. With private endpoints, Praveen also has the ability to choose which clouds he wants to deploy his endpoints to. He can choose to deploy his endpoint to his AWS, GCP, Dev, Stage, Prod, or even a hybrid cloud to meet his application needs. He can choose to run his LLM application in an isolated cloud to meet strict performance requirements in a single tenant setting. Private endpoints also gives Praveen more control in knowing what's happening with the underlying system. I've jumped to another private endpoint that we deployed early last week to run very large-scale load tests. You can see that private endpoint has the Llama 2 family of models deployed, the Llama 2 chat models, the 7 billion parameter, 13 billion parameter, and 70 billion parameter models deployed. If I scroll down, I can see the API and how I can actually integrate private endpoints into my application. It's completely compatible with public endpoints and very, very easy to integrate into your application. But what Praveen also gets from this page is a link to a real-time dashboard, providing him a deep understanding of what's happening with his underlying system. He can see important metrics, for example, the cluster utilization, the volume and traffic that his application is serving, any errors he may have that he may need to diagnose and go into logs to investigate, and important latency measures at the P50, P90, or P99 level, and so much more. This sort of control gives Praveen the confidence he needs to run his LLM application in production. Now, the last element that Robert touched on, beyond privacy and control, was customizability. And this is another area where Anyscale private endpoints shine. At the beginning, you saw as I created my endpoint, I had the ability to choose which models were deployed, including custom fine-tuned models. That functionality also extends to me being able to update the models that are deployed to my endpoint. Perhaps over time, your LLM application integrates new functionality and you need to add new models. Or you get new data and create a new fine-tuned model that you want to add to your endpoint and remove an older version. With Anyscale private endpoints, you can. And in fact, as you do that, Anyscale automatically handles finding the right instances and accelerators across clouds to make sure your endpoint solution runs reliably, cost-effectively, and with the performance you need. And you can see that even more importantly if we scroll back up, the traffic for my application continued unabated. There was no interruption for my end users. So I was able to update and customize my endpoint with zero downtime for my end users. Now we realize there's some customers out there who want very specific control over hardware and using certain instances or accelerators. With Anyscale private endpoints, they can get it. Here's an example of a configuration that I used where I wanted to run my LLMs on a very specific set of hardware. With Anyscale private endpoints, I was able to choose the exact instances, capacity reservation, accelerators, and scaling behavior that I needed to run my application how I wanted. And there you have it. Anyscale private endpoints provides the same great experience, performance, reliability, and scalability of Anyscale endpoints, plus the privacy, control, and customizability you need to run your LLM applications. I'm really excited to see the applications you all will build with Anyscale private endpoints. Thank you.
Great job. Thank you so much. We have a lot lined up for you over the rest of today and tomorrow. We're going to be hearing from some incredible speakers. We'll be hearing from John Schulman, one of the co-founders of OpenAI and the creator of ChatGPT. Ben Horowitz, one of the co-founders of Andreessen Horowitz. LangChain creator Harrison Chase, as well as engineering leaders from so many different companies, from LinkedIn, Niantic, Adobe, Airbnb, Uber, about how they build and deploy LLM and generative AI applications using Ray. These are some of the people moving the field forward. If you're looking to accelerate LLMs or generative AI in your business, I don't think you could be at a better event. With that, I'm very, very excited to welcome John Schulman to the stage. John is one of the co-founders of OpenAI and the creator of ChatGPT. Please welcome John. John, thank you so much for being here.
Pleasure to be here.
So there are a bunch of questions I'd love to ask you about your work at OpenAI. But before we dive into that, can you tell us a little bit about how you got excited about AI in the first place?
I used to read a lot of sci-fi as a kid. I liked Isaac Asimov's books and Werner Vinge.
Yeah.
And I remember picking up The Singularity is Near by Ray Kurzweil at a garage sale once and looking at all the nice scaling plots, like how Moore's Law and all of its variations. Mm-hmm. So, and then I did some projects as an undergrad in doing things with machine learning. Like I worked on transcribing handwriting into LaTeX for some project, for some class, and that was exciting to me.
You also did some physics projects, right?
Yeah. Oh yeah, I did an undergrad in physics.
Okay, nice. And so that led you to do a PhD in machine learning, right?
Yeah.
Now, you weren't always working on language models, right? Can you tell us about the kind of work you did in grad school?
Yeah, I started grad school in neuroscience, but then I ended up switching to robotics, to a machine learning group, Peter Abeel's group that worked on robotics. And so I worked a bit with the robots of the time. Like there's the PR2, Personal Robot 2, and we were doing things like using it to fold laundry in a very slow and deliberate way, and I was working on tying knots, getting it to tie knots.
I remember that.
As a kind of simulation of doing robot surgery. That was the motivating application, like having suturing with the robot.
Yeah.
So yeah, I worked on robotics a bit for a while, and then halfway through the PhD, switched over to reinforcement learning.
If you look back on your PhD work, I'm curious, which projects do you think stood the test of time the most?
I'd say the work on reinforcement learning and specifically applying it to neural nets, definitely, that was the stuff that then ended up making a difference in the long run. Some of the earlier work on robotics definitely produced some nice demos at the time, but I don't think the methods are that general.
Yeah. Cool. So we all know that OpenAI does great research and builds great products. But OpenAI didn't start out that way, right? It started out purely focused on research, right? Mm-hmm. Can you tell us about that transition? What led to the decision to do both?
Well, we were interested in releasing some kind of product or releasing something to the world from the beginning, but we also didn't want to go too far out of our way to build a product. So there were some ideas being tossed around, but nothing quite came together. And we wanted to raise more money, and it was kind of, even though our structure didn't require us to make money immediately or be profitable, it seemed like we were going to be able to raise more money if we actually had some kind of product out there. And also we felt like it was, it's nice if your research actually connects to the real world instead of just being kind of, I don't know, just having, just being like publishing things and putting together demos.
Yeah. And so your first product was the API product, right? How long, once you guys decided to start building products and shipping that, how long did it take to decide on building an API? Were there other ideas you considered?
Yeah, we had some other ideas. A lot of them were more like domain-specific applications, like doing translation. So after GPT-3, we knew that these models were impressively smart, and there must be something you can do with them. So we ended up thinking about a bunch of natural language processing applications, but at the time we were thinking that the model wasn't quite good enough at anything to be useful by itself, so we would probably need to fine-tune it and build it, make it really good for a specific application. But I think then there was the other, I actually don't think we could have succeeded with one of those products because it would have required building up a ton of domain expertise and really digging into that domain, and it would have been, it would have required a lot of work that's separate from our main research. So the nice thing about an API is it's just basically taking the thing that the research team has built and commercializing it directly, as opposed to going and building this whole other product that's separate from what the research team is doing.
Were you deterred at all by the fact that there were other AI APIs out there? Other companies have tried building AI APIs, but none of them had been a huge success?
A little bit. That was definitely a concern, that there were some other APIs like for object recognition and vision, and I think some of them were moderately well used, but they weren't spectacular products. So we had some concerns about that, and I think in retrospect, those concerns were warranted because I'd say the original model we released the API with wasn't good enough for most people. I mean, it was a pretty small business for a while, and I think it only, the model started to get good enough only in the last year and a half or so.
So it wasn't an overnight success. When did you realize that it was going to work out, that the API was, the right choice, or that it was going to work out?
Well, I think you could have looked at the trends and predicted what I just described, that maybe the initial model wasn't good enough, but some future models would be. And like serving models seemed like a generally useful thing to do. So I would say that the API only saw a lot of growth in 2022, just after we had the GPT 3.5 based models coming out, and then we sort of had a pretty steep growth curve. And then ChatGPT itself made the API a lot more popular because a lot more people got excited about language models in general.
Yeah. Now, before we talk about ChatGPT, let's talk about scaling. This is a distributed systems event in some extent. We all know OpenAI uses a huge amount of compute. And actually, I think OpenAI was perhaps the first to really go all in on scaling. Where did that belief in the importance of scaling models and compute come from?
The idea that bigger models are better was a bit in the zeitgeist, that people had produced the best benchmark results with fairly big models. And, but I guess it wasn't, and I would say the founding team of OpenAI was leaned more towards this aesthetic of scale up simple things rather than trying to build some complicated, clever thing. Like, we definitely believed that simple things that are doing the simple thing right was tended to win in machine learning. But I would say for scaling, it's not, scaling looks easy when you see the final result, or it looks obvious when you see the final result that like curve goes up and to the right, but often there's a lot of complexity in getting there, and you have to say, I mean, there's all the systems, just doing the engineering is very difficult to get something that's actually performant at scale. And then there's usually all these little details, like you have to scale your learning rates just right. Otherwise, you get worse results with big models, and you have to scale your data up along with the model size. So I'd say that it took several years to figure out what were the right recipes for scaling things.
Yeah. Now, we talk about scaling as if it's one thing, but there are many different dimensions you could scale, right? The amount of data, size of the model, just the amount of compute you put into it, maybe other things as well. Is it obvious which ones matter and which ones don't?
Well, it's usually not completely obvious. I mean, model size and data are the two biggest ones, but then you usually have a lot of hyperparameters that have to be scaled properly, and it's you have to do a lot of science to figure out how to scale them.
Yeah. So can you share some intuition about why scaling is hard? Like, why aren't we using much? What's stopping us from using 70 trillion parameter models today, or even bigger?
Yeah, I think a lot of that is about, well, it's about compute efficiency. Like, you can, so now we know you can train a small model for really long or a big model for short, and there's some trade-off, and it turns out that somewhere in the middle you get the best compute efficiency. So if you put the flops on the x-axis, you have a bunch of curves of, you draw your learning curves of loss versus flops. There's some optimal model size for getting the best performance. So I think what we have now is just using transformers and using the training recipe we have, it turns out certain model sizes are the most efficient given the amount of compute resources we're putting into it. But that's probably going to change as we start putting more compute into the training runs, and also maybe as we start to change the training methodologies and the types of data we use, we also might find that different size models end up working the best.
Do you have a sense of whether this is something with diminishing returns or not, like how far this will take us?
Yeah, I'd say often the returns diminish as you scale the current thing, but then there are other innovations that let you continue. So I guess I don't see deep learning in general reaching a plateau or anything, or hitting diminishing returns. Maybe just doing the most basic thing reaches some diminishing returns.
Yeah, makes sense. Since this is Ray Summit, let's talk a little bit about distributed systems and infrastructure. So I'm sure almost no one in this audience knows this, but early on, or maybe partway through your PhD, you actually built your own deep learning framework called Computation Graph Toolkit. Can you share a little bit about why you built that and what you were trying to achieve?
Yeah, some people might remember Theano. That was this.
Absolutely.
That was the AutoDiff framework from before TensorFlow and PyTorch. So Theano was amazing, but it also was starting to hit its limitations. Like it would sometimes take half an hour to compile your graph before you could do a single step. So, and I wanted to do some things like I wanted to do some things with recurrent networks, and Theano wasn't that great for it. So I ended up working on building one of these things. And actually, I think it was a great learning experience. I mean, it turned out that Google, there was TensorFlow and PyTorch right after that, and those ended up.
I think you were working on CGT. This was 2015 in the fall, and then TensorFlow came out right after that.
Yeah, I started working on it before I knew about TensorFlow, and then I found out about it, and maybe part of me was disappointed that I was getting upstaged by Google, but it's fine. Yeah, I think everyone should write their own AutoDiff. Everyone should at least write their own little AutoDiff library at one point to get a really good intuition for backprop.
It's a great idea. Yeah. But this is all, the slow compile times for recurrent neural networks. This is, I had forgotten about that. That was a long time ago. But if I remember correctly, it was quite fast. It was actually, quite well architected. And you actually were an early Ray user, or maybe you attempted to use Ray. You used Ray quite a long time ago, before it was really ready. Can you share, do you remember what you were trying it for and what your experience was like?
Yeah, this was back in 2016, 2017, when you guys were just getting started on it. Yeah. And at the time, I was doing something in the realm of architecture search. And I remember creating some issues on GitHub about the scheduler not doing the right thing, which you guys have fixed since then. But
it's come a long way. There's still GitHub issues, so probably
you closed that issue at some point. So I remember seeing a
so it must have gotten
notification
fixed.
about it. Yeah.
Nice. Can you share a little bit about, you guys are pushing the limits at OpenAI of scale in a lot of different dimensions. And so you may encounter challenges that a lot of other people don't encounter. Can you share a little bit about, what makes infrastructure hard for the kind of AI work you guys do at OpenAI?
Yeah, we have a library for doing distributed training, and it does model parallelism. So you're sending around weights and gradients and activations. And Ray, and we use Ray as a big part of that for doing all the communication. And it's been very useful having this solid component that we can build on. We've had various, OpenAI has a lot of the type of people who like writing their own distributed systems code.
Yes, so
we've had our own, everyone likes writing their own thing. We've had our own internal libraries. Often when you develop something internally, it works great for the person who wrote it, but that person usually doesn't want to maintain it for years, and it's not very well documented or general. So we've had our own internal systems, but then I'd say it's been nice switching over to Ray, so we have this solid component that is very well documented and supported that we can build on.
Yeah. So if you weren't using Ray, what would you be using?
Yeah, we'd probably we'd probably roll our own thing and use tools. We'd use the other lower level tools out there like Redis and MPI and so forth, and just glue those together.
Yeah, lots of MPI, lots of Redis.
Yeah.
Makes sense. Nice. So tell us about ChatGPT. How did you get the idea? When did you start working on it?
Yeah, so I'd say it started off, well, I personally was working on a project called WebGPT before this, which is like a question answering system that does retrieval, and so it'll you ask a question and then it'll go and find a bunch of relevant sources by doing a web search and browsing some of the pages it finds, and then write an one or two paragraph answer with citations. And this was what we were trying to get at with that project, was getting language models to use tools and like we were trying to work on this problem of truthfulness. Like, how can you get models that don't make stuff up? They just say things that are true and based on.
Has that one been solved?
I'd say we made progress on it. It's not completely solved, but yeah, we've come a long way. So yeah, we were really interested in truthfulness. So that project, we had worked on this project and we had published a paper about it, and we're trying to figure out what was the next version of it. And for question answering, I'd say chat starts to make a lot of sense, because you need to do things like follow-up questions and clarifying questions. And and there were some internal, we had been playing with chat internally a bit, like at OpenAI, and it seemed like the models were quite good at it. So yeah, we decided to have a dialogue-based system for the next iteration of our system. So we started collecting data in like early 2022 that was like specific for chat. And we were originally, it was going to be a successor to this WebGPT system. And eventually we really ended up liking the chat models, and the whole retrieval part ended up being a little complicated. So we temporarily dropped that, and we just decided to focus on the chat models. And I'd say we were surprised by how good the models were, or how useful they were. So we had an internal demo, and I definitely used the demo a lot for coding help, because the models are really good at answering questions about code, especially when you're trying to use new libraries. So yeah, it became, we started to think that it was a good idea to release, to like do a public release and just let other people try out the model. And that ended up getting delayed a bit, because we had GPT-4 finished training, and everyone got excited about that model. And the chat model we had trained that was based on GPT 3.5 was that kind of got sidelined for a while. But anyway, we ended up deciding to do a release anyway, and worked with the product team who put together the UI and everything for it, and then ended up launching it late in November that year.
It was a great decision.
Yeah, it turned out.
Were you surprised by just the world's reaction to ChatGPT, or given that you had a lot of experience using it internally, did you kind of see that coming?
Yeah, we were very surprised. I mean, we did have beta testers, so we had friends and family using it for a few months beforehand, and there were definitely some enthusiastic users, especially people using it for code, but it didn't really, I don't know, people weren't that excited about it, and not everyone ended up, not all of the users ended up coming back to it a lot. So only a few of the people who we gave access ended up using it regularly. So I think what happened was, when everyone got access, people sort of taught each other how to use it and what use cases ended up working. So it was kind of the social aspect of it was pretty important. Like, people teach each other how to prompt it and what kind of tasks it's good at. So I think it really, just the fact that it was really easy to use and people could share their use cases with each other caused this mass excitement.
Yeah. So you mentioned using it for help coding. What about today? What do you use Chachi Beauty for today?
I'd say that's still my biggest use case personally. I also just use it here and there as just to ask questions. If I have random questions about history or science or whatever, I'll just ask it. But I'd say the one I get the most utility out of is coding.
Yeah. So you've been in AI for quite a long time. If you look back on your time in AI, more than a decade, what do you think of as the biggest advances or conceptual breakthroughs that have happened during that period?
Well, yeah, I guess I started grad school in 2010, so that's when I was sort of seriously in the field. And I'd say back then, well, deep learning hadn't really taken off.
Yeah.
So it wasn't even clear. I remember thinking that it wasn't clear what you would use neural nets for. Like if it wasn't clear that making the model that we would even know what to do. If we had a model that had like a model that was more powerful, it wasn't even clear exactly what we would do with it. So I would say there were a lot of things that were less obvious then. Like we didn't know deep learning worked really well. We didn't know exactly what training objective you would use. If we did know that neural nets could be trained, it wasn't clear exactly what to do with them. And so I guess the answer there ended up being fairly simple. Like whatever, like you can do reinforcement learning with neural nets. You can train classifiers. You can do maximum likelihood on sequences. And all these things work pretty well. I mean, some things that were popular back then didn't end up working that well or didn't scale as well. So yeah, it's kind of the set of things that ended up scaling wasn't easily foreseeable at that time, but yeah.
And certainly the importance of scaling.
Oh yeah, and definitely scaling, yeah. The fact that scaling was so important and the whole paradigm of scaling laws.
Yeah. I'm sure you probably took an introductory machine learning class at some point, right? And at least, I don't know about now, but a decade ago when they were teaching introductory machine learning courses, the course would often start by framing different areas of machine learning. They say there's supervised learning, which is like classification and regression, and there's unsupervised learning. And when we talked about unsupervised learning, at least when I took machine learning, it was mostly about clustering, like k-means clustering and things like that. I feel like, I'm curious if you would agree that our perspective on unsupervised learning has changed quite a bit over the past decade.
Oh yeah, definitely. I mean, now it's not even clear what unsupervised learning means. Sequence modeling is like the way the language models are trained. Is that unsupervised learning? It's kind of supervised by predicting the future given the past.
It still fits into the regression framework, or classification framework, but you don't have to spend a lot of energy labeling data and things like that.
Yeah.
But yeah, it's not k-means clustering, that's for sure.
I mean, you can say that supervised learning is a special case of unsupervised learning or doing maximum likelihood.
So I think, looking back a decade ago, problems like unsupervised learning were not that well understood, or perhaps we didn't know how to conceptualize the problem. What do you think are the problems today that we're still figuring out how to formulate?
I'd say there's a lot of problems around, I'd say one problem I ended up thinking about a lot is data quality and like how to get really good supervision. So like GPT-4 is really good at a lot of things and it has a lot of breadth of knowledge, and it's often hard to even collect good labels to make it better. Like if people ask it questions about, they ask about all sorts of obscure topics or very technical topics, and it's hard to find people who can label this, who can provide good labels. So there's this problem of how do you supervise a model that's kind of superhuman, and I would say sometimes this is called scalable oversight or scalable supervision. People first got interested in this from the standpoint of alignment and how do you make, concerned with like the very smart models and how do we make sure they're doing doing what humans want. So I'd say in this area, like some of the problems haven't even been formulated precisely yet.
Yeah. So you have good taste in problems and what to work on. How do you decide what problems to work on?
Yeah, I don't think I have a really general framework for doing this. I try to think about some real-world use cases and what are some common limitations of our existing methods that would unlock a lot of opportunities. And I try to think of the advances that would feed into a lot of that would have a lot of downstream implications.
And are you thinking about how we get to human level intelligence and kind of working backwards from there, or thinking more about products that could be built or applications?
I'd say I do a little bit of all of those. I mean, I'm thinking about what humans can do and how the human mind works, and like trying to introspect is useful, but it can also be misleading. So I think it's useful to think about where are humans much better than our models and where we might be missing something. But it also, it's hard to predict what order we're going to get AI to solve different problems. Yeah. And if something is, how hard something is for humans doesn't necessarily correlate that well with how hard it is for AI. So
math is hard for both of us.
Right, definitely. Yeah, so that's one.
Yeah.
Yeah.
So when you think about the path to, say, human level intelligence, do you think of it as more of a research challenge, an engineering challenge, both, or does the distinction not make sense?
Yeah, I'd say it's both. It's a little of both, and the boundary is a little bit blurry. Like, definitely, you need to do a lot of engineering to get more data and train bigger models on that data, and then there's a lot of research for like how you can to just make that scaling work. You need to figure out the recipe of how all your hyperparameters scale, and then there's open questions about things like data quality and supervision that I just mentioned.
And you mentioned high quality data. In your view, when a human is learning, right, how much high quality data do we have access to, like in a normal educational experience? Like how much like when humans are learning, like learning from their parents or schools and so forth? Like, yeah, I mean, we have access to tons of data, right? Both things like textbooks as well as just all the sensory input that we get in. Mm-hmm. Do you consider some of that high quality and some of that low quality? Oh yeah, well, I guess human learning, humans are extremely, I guess humans are able to learn from very undiverse data. So I think one of the most remarkable things is that a human can grow up in spending most of their time in one household and talking to a small number of people, maybe going to school. So there's not a lot of data diversity compared to what we train our systems, deep learning systems with. But still you get an extremely robust model, like a extremely robust vision system, even though you've only seen this one house. So that's pretty crazy, and I think we're nowhere near. There are limits to that, though, right? If you never see vertical lines or something like that, Yeah. This has been fascinating. Are there any common misconceptions that people have about OpenAI that you'd like to clarify for us? Yeah, I'd say sometimes I read Twitter and people are talking about Chachi Beauty and they have some speculations about what we're doing, and sometimes I think, sometimes people have some
well, people often think we're doing a lot more than we're actually doing. Like they think we're monitoring everything, like monitoring Twitter and usage in real time and fixing the model, like fine tuning all the time and fixing all these problems. And yeah, I'd love to do
Like the jailbreaks.
Oh yeah, fixing jailbreaks and like finding when the model gets a riddle wrong, and we're going to go and fix that. So yeah, it's more like we love to fix things faster, but it's often hard. Like you can't, you don't want to just play whack-a-mole and fix these little problems. I'd rather like look at the bulk of use cases and make everyone's experience better. So it's more like when we get feedback from people, like they give thumbs down, we use that as part of our data labeling effort, and we try to collect some labels to fix those examples. But yeah, I'd say that's, yeah, people also, yeah, people think we're doing all sorts of crazy things that we're not doing. But.
Glad to hear it. Yeah, John, it's been a pleasure. Thank you so much for being here. Really enjoyed the conversation. Everyone, please join me in thanking John Schulman.
I guess I will. Thanks for having me.
Yeah. You can just take it out now. Thank you so much, John. Next up, I'm delighted to invite Ya Xu to the stage. Ya's VP of Engineering at LinkedIn and Head of Data and AI. Please welcome Ya.
Hello. What amazing talk and fireside chat. All the crazy and amazing things that they do at OpenAI. But I am mostly excited about, I don't know what you all caught, John mentioned about this laundry folding robot that he worked on. That would be my request to him. So great to be here today to share with you a bit of what we do at LinkedIn, just a little bit of a journey that we've taken over the years. We're going to cover a bunch of AI-powered products we have, go into a little bit of a tech focus that we have right now. And of course, at Ray Summit, we've got to talk about Ray. In case anyone in the audience doesn't know what LinkedIn does, just wanted to highlight, we are really focused on creating economic opportunity. And of course, thinking about the entities that we have on our economic graph so that we can do that, right? We have lots of members, schools, companies, we're very vibrantly interacting with each other with tons of posts and job applications that's happening throughout our platform. And of course, to power all of that is AI behind the scene. Not surprisingly, lots of our products using AI deeply, and starting with search. I think nobody here is surprised to hear that obviously search has been the, I would say, very first industrial scale AI application across, and LinkedIn is doing the same as well. People search, job search, that a lot of you who are using our consumer product is very familiar with, but also with our enterprise product where we search for courses, search for candidates, for recruiters, and search for leads on our platform for sales people as well. And recommendations, another really important aspect of our platform, of our products, recommending posts for people to read, jobs, recommending candidates for recruiters, recommending people that you may know that you want to connect with. In addition to those obvious I would say user-facing products, a lot of our marketplace design also relies heavily on AI as well, going from bid suggestion, budget recommendation, forecasting, pacing. A lot of what goes into making marketplace work also relies heavily on AI. Of course, everything, we have to take trust and responsible AI deeply, from defending and identifying, detecting bad actors on the site, the bad content, all the way to making sure that as we are creating economic opportunities, that we really are considering that for every member in the workforce to be fair, transparent. A lot of what you heard Robert talk about earlier with regarding privacy concerns, how do we use differential privacy, and federated learning is also part of what we do as well. And of course, we cannot go on the talk today without talk about generative AI. Ever since about a year ago, we have really started to build a lot of generative AI capabilities on our product as well. I would like to think about how AI products in the past mostly working a little bit more in the background, where you have the product and user experience, and you kind of like, talk to AI in the background. But now, AI really has become the product itself, and it's coming from really the background to the foreground. And we have been working on that very deeply over the last year or so. And starting from, as you can see in the demo here, we are helping members to write their profile better with generative AI, to really streamlining hiring process with automatically generated job descriptions as well. Not only just like generating you with a job description, but also helping recruiters as they are writing that job description to leverage the skill graph that we have to be much more customized in the description that they're creating. We're also helping recruiters write better emails, taking into consideration of both the candidates they're writing email messages to, and also the company that's hiring the job that they're hiring for. So all these are coming together in our product suites, and we are building way more as well. Of course, powering a lot of the experiences you just saw needs a lot of technology behind the scene as well. A few of the things that I'm just gonna touch upon 3 challenges and opportunities that we are working on. Starting with AI productivity. This may not be a fancy topic to talk about, but a lot of you who spend a lot of time developing AI product also know that AI development is very different from traditional software development process, right? Traditionally, we have, when we develop software, it's by and large, a very linear process. But AI development is highly nonlinear, right? It's very iterative. As an example, in order to launch one single model in some of our product suites, it takes over 100 offline iterations, and it takes 30 plus online iterations in order to ship one product to production, right? Some of those offline iterations takes hours, if not days, to run. So in order to really leverage AI and then having this to be magnifying the impact that AI can create, getting AI productivity into a better state is a very important line of work that we do. And this really goes across multiple different aspects, right? Reducing training time, and be able to leverage a GPU training, incremental training, a big effort that we're spending time on, and reducing a lot of the toil that we have in our model development process, right? And also be able to simplify our feature generation is all the 3 aspects are areas that we are spending a lot of time on. We spent a lot of time, as you heard earlier, talking about LLMs. Obviously, those large models, they are really needs a lot of our infrastructures to be able to support, to train, and to serve them. But I also just wanted to remind everyone here that LLM is not the only large models that powers every line of AI work that we do. A lot of the data that we have are not languages, right? They're not contents. They are engagement data, I liked a post, I sent a message to somebody, I connected with somebody. All this comes in a form that is not languages, but in a more of a tabular or sometimes graph structured data. So we do work heavily on a couple of other architectures that can really help us harness the value of the data in the other formats. And we call them large personalization models and graph neural network. And really, they're just, I'm barely touching the surface, by the way, so please feel free to reach out to me afterwards if you wanted to learn more about it. But really being able to scale our training to be able to train those models within a reasonable amount of time. And it takes a ton of effort from both our infrastructure, network, and from and the algorithms as well in terms of how we're batching them. And the LLMs and LPMs actually also takes very different sort of infrastructure needs, right? LPM is so much more memory constrained than compute constrained, as example. And serving them is also obviously very different, right? You have LPMs that takes a lot of embeddings and then being able to have distributed memory to be able to serve them. And is, again, is quite different from LLMs as well. So lots of work that goes on in that space in order to push the boundaries. And we really have made a lot of strides around getting our models to be bigger and be able to serve those bigger models, but there's just like a lot that we can do in that space as well. And last but not least, generative AI, right? I mean, this is really the buzzword of everyone have been hearing. Robert earlier mentioned about there are companies who have been developing AI for years, I feel, but then really also just reevaluating everything that we're doing because generative AI does take a very different stack in order to serve them, in order to train them as well. And here, as example, is what Kevin Scott shared at the recent Microsoft Build conference, talking about in order to build Copilot, right? You gotta have the right front-end stack, you're gonna have the strong orchestration stack, and of course, the model stack as well. And recently, very popular blog post on A16Z also have outlined just how expensive in order to serve those LLM apps and what's needed. And I'm just gonna quickly go through what we have been building as well, and then just kind of walk you through a little bit of the stack. Starting from Gateway, we serve both internal models and leverage heavily of OpenAI models as example. So having a gateway that is able to serve those models, doing quota management, and monitor utilizations, and then being able to do responsible AI checks are really important. Orchestration layer, we build on top of LangChain, and also being able to we all know there are limitations of LLMs. A lot of times, hallucination, being able to ground it with the data, being able to integrate closely with the data that we have is, using various different internal APIs and tools that we generate, that we have, is really important. So that layer is able to select the right tools. Doing retrieval augmented generation is very important. Memory, obviously very important, but also it's not just memory, but also being able to do embedding-based retrieval where you can compress a lot of the context from the past conversations, be able to kind of pinpoint where the part of the conversation that's most important and the examples that you can leverage in order to respond in the next turn of iterations is really important as well. And of course, model training, fine-tuning, domain adaptation, all these are important layer that we need to build internally as well. Serving models, as those models get much bigger, they definitely takes multiple GPUs and a lot of times multiple machines in order to serve them. Trust and responsible AI, another very important aspects of our AM app stack, being able to detect the prompt injection, jailbreaking, and a lot of our just the trust layers that we usually apply to our general AI applications. All these are really important as well. Of course, also a lot of developer tools, being able to help our developers to be much more productive, to be able to do prompt, playgrounds, and evaluation are also really important. And a lot of this, I would say that even though that we have a lot of experience building AI applications that are very, I would say functionally very similar to the list that I've included here, but because LLMs work differently and these layers all need to be extended and iterated on in order to make this work for LLM applications better. Okay, so last but not least, let's talk a little bit about Ray. As you can tell with a lot of the scale that I just described and the applications that we built, we heavily leverage Ray for our training stack for hyperparameter optimization. The part where Ray came in really handy, not only because a lot of our models itself, the single models, needs tuning, but also we a lot of times have to trade off across multiple different objectives, right? This thing we call MOO, multi-objective optimization, is you also need to be able to tune the weights when you are combining different objectives together. And for that reason, we heavily involve Ray in our tuning and our training stack in order to scale and really helping our AI engineers to be much more productive as they're building those models. And also, we talk about how inference is no longer simple, right? So traditionally, when we are building our search and recommendation stack, you have your model, you maybe have a L1, L2, and you kind of have some business logic on top of it. And it wasn't so complicated. But as you can see in these graphs that we talked about earlier, LLM inference is a lot more complicated. And so in order to do those ML apps that we're building, you will have multiple models, some of them doing intent detection, some of them needed to do multiple different sub-models that the intent layer can then route to. So in order to orchestrate all that model serving, we heavily rely on Ray, as Ray serving in particular, that is able to help us to break the inference graph in a much more atomic level, at the same time also be able to optimize our usage between our CPUs and GPUs, etc. So really a great piece of infrastructure that I have built that we are able to leverage. If you wanted to hear more about how we are using Ray, we do have a couple talks this afternoon, one by Sasha and Ali, on talking a lot about inference graphs at LinkedIn, and Frank, Mingyang, and Wei is going to talk about hyperparameter tooling and how we are integrating it in our training stack this afternoon as well. So I really highly encourage you all to attend their talks. And with that, thank you for spending the time, and I'm going to hand it over, I believe, back to Robert.
Please welcome to the stage Executive Chairman Anyscale, Professor at UC Berkeley, Jan Stojka.
Good morning, everyone. Since we had our last summit 1 year ago, many things happened. And of course, chief among them has been the LLM revolution. ChatGPT was launched just 2 months after our last summit. And it went to become the fastest growing consumer product, reaching 1 million users in just 5 days and 100 million in just 2 months. And in the process, achieved significant milestones. First, it's performing now well enough so it can pass the bar exam. And in the form of the copilot, it can double the programmer productivity. So what else has happened since then? First, open source models are catching up. This is a leaderboard we developed at UC Berkeley to evaluate the most popular chatbots. And as you can see, while the proprietary models are still at the top of the leaderboard, the open source models, here with yellow, are not far behind. One reason open source models are becoming an alternative to proprietary models is fine-tuning. You heard about fine-tuning early on. Let me tell you a little bit more. So here are 3 relatively common LLM tasks: functional representation, natural language to SQL translation, you have heard about that a few times already, and a mass benchmark. And with light gray, we have the accuracy of GPT-4, and with blue, the accuracy of the smallest Llama 2 model. As expected, GPT-4 performed much better. There is really no competition. However, if you fine-tune the open source models, things change. Their accuracy in 2 out of 3 tasks exceed of that of GPT-4. And for the last task, the mass benchmarks, you can actually bridge the gap considerably by using the largest Llama 2 model. So in summary, fine-tuned OSS open source model can outperform GPT-4 for some important practical tasks. Now, this is a plot I shared with you last year, and it basically shows that the compute demands to train the largest model have grown 10 times over every 18 months since the beginning of 2010. At the same time, the Moore's law is growing just twice every 18 months. And actually, as you know, the Moore's law has slowed down over the past 2 decades. So actually, the gap between the demand of these models and capabilities of this a single node or a single processor, it's even bigger than this plot suggests. So what happens over the last year? Well, here is the GPT-4. So as you can see, the growth in the demands of these models has been growing unabated. Again, this means that there is no way to scale these workloads but to distribute these workloads. This was true last year. It's even more true today. And this, of course, has an impact on the costs. GPT-3 was released in 2020, and it cost between 4.6 million and 12 million to train, depending on what source you are using. 2 years later, GPT-4 was released, and according to Sam Altman, it cost over 100 million to train. So an increase between 8.8 and 22 times. But things are even more challenging. Even if you have money, you may not find GPUs. The GPU shortage has been so severe that it has impacted the roadmap of GPU-rich organizations like OpenAI. So what has been the consequence of such severe shortage? First, this scarcity presents a big opportunity for hardware vendors. So more and more of these vendors have introduced or announced new hardware accelerators for AI over the past year. Second, over the past year, we have seen the emergence of more clouds. In addition to the big 3, AWS, Azure, and GCP, we are seeing more and more clouds which targets to alleviate this scarcity of GPUs by providing more GPU capacity, often at lower prices. And as the LLM models become more and more powerful, the applications are becoming more sophisticated, more complex. Here again, you just seen that. This is the LLM application stack according to A16Z, which was published a few months ago. And you can see it's quite complex. There are 15 boxes in this diagram. And here is another diagram for a canonical LLM application, again, quite complex. So while LLMs are holding a huge promise, there are three challenges that are threatening their evolution. First, the growing complexity, which is driven by the increasing heterogeneity in hardware and in the clouds, as well as the growing complexity of the applications themselves. Second is the increasing scale, and finally, skyrocketing costs. Now, Ray holistically addresses all of these challenges. The central component of Ray is Ray Core. And Ray Core is an operating system for heterogeneous distributed computing. Because its generality, it supports virtually any AI workload, including all LLM workloads. And to make it easy, it provides several libraries: serve, tune, train, reinforcement learning, and data. So with Ray, instead of using different systems to scale each of these workloads, and then stitch together the system for your end-to-end application, you need to use only one system. So Ray provides you a unified framework for all your application workloads. In addition, we have been working hard to make it as easy as possible to run your Ray application on a diverse set of clouds and hardware accelerators. And finally, from day one, we built Ray to scale from 1 node to hundreds or even thousands of nodes. So perhaps not surprising, given Ray's ability to address the LLM challenges, since last years, Ray's adoption has accelerated. The number of GitHub stars has been growing faster than ever, and this is compared with other very successful open source distributed frameworks. The number of contributors increased by 25%, the largest year-to-year increase we have seen. But most impressively, the number of Ray clusters has increased 6 times just from the beginning of this year, so in 10 months. So what we focused on over the last year? Well, not surprisingly, we focused on further addressing the LLM challenges I just mentioned. Reducing complexity, improving scalability, reducing the cost. So let me start with the work we have done to reduce the complexity and improve the scalability. First, we had improved the scalability and stability of KubeRay. So now you can deploy any Ray application on any Kubernetes cluster. And the growth in adoption was outstanding. Since the beginning of the year, the number of Ray clusters using KubeRay has grown 15 times. Second, with RayServe, we have focused on simplifying the development and deployment of the LLM services. To do so, RayServe provides support for composing models, the ability to serve large models on multiple nodes, to combine business logic with the inference, and provide support for streaming outputs to make it easier to build chatbot applications. And when it comes to scale, Ungroup has been running RayServe in production over 4,000 GPUs and 500,000 CPUs. And since the beginning of this year, the number of RayServe clusters has increased 6 times. Finally, with RayTrain, we focus on simplifying the task of fine-tuning. RayTrain provides support for distributed training and high parameter tuning, high-speed data ingestions, and support the major machine learning libraries, including PyTorch, TensorFlow, Hugging Face, DeepSpeed. Since the beginning of the year, the number of RayTrain clusters has increased 10 times. These libraries are used today by hundreds of organizations. And I'm very excited that a few of these leading organizations are here at the Ray Summit to share their experience with us. Finally, I'm very excited to announce that KubeRay, RayServe, and RayTrain are all now generally available. So now let us turn our attention to reducing the cost. I will illustrate 3 ways Ray enables you to reduce the cost. By exploiting resource heterogeneity, Ray's flexibility, and finally, taking advantage of state-of-the-art accelerators. First, consider a batch inference, a typical AI application. Here, we first load the data, then we pre-process it, then we perform inference on the data and save the results. Because of Ray flexibility and generality, we can implement the entire pipeline on top of Ray. In addition, what Ray allows you is to run different stages of this pipeline on different hardware. So you can run the data stages on CPUs and the inference on GPUs. And by doing so, what you get, significant cost savings. For instance, in this case, to process 1 million images, you pay only $3.5 on AWS. To do the same with the leading open source framework, you can pay almost double, $7.3. And if you want to do this with a leading machine learning platform, you can pay 16 times more. So huge cost savings. Here is another example from our friends from Samsara. They have a serving application. They implemented it using a microservice architecture. Again, it has 3 stages. In the first stage, you get the query, you use some business logic to select the model to serve that query, and you do some data processing. In the second stage, you are going to compute the embeddings, and you are going to use the model you selected on that query. And finally, in the last stage, you are going to use some business logic to filter the results. The first and the last stage are implemented in Go, and the stage in the middle, the inference stage, is implemented in Python. The Samsara engineers, they took these applications, redesigned it, and re-implemented it on top of Ray. Again, because of Ray generality and flexibility, they could implement the entire pipeline on top of Ray in a single system. And because they've done that, they can obviate the need for expensive serialization and deserialization between these stages, as well as more efficiently share the resources across these different stages. And by doing so, they reduce the cost by 50%. With the advent of this new hardware accelerator, developers have now more choices than ever to further reduce the cost for certain workloads. To enable Ray developers to do so, we have been hard at work which adding additional support for the new hardware accelerators. In addition to NVIDIA GPUs, now Ray supports TPU pods from GCP and is going to add support for AWS Inferentia and Trainium in the next release, and support for Intel Gaudi by the end of the year. You can hear more about this integration tomorrow during a special keynote on hardware accelerators. So I hope that by now, I convince you that Ray is a perfect framework to build, scale, and deploy all your AI and LLM workloads. However, as good as Ray is, AnyScale is even better. And why? Because AnyScale is the best place to develop and run Ray and LLM applications. Before you hear more about AnyScale Platform, let me give you some teasers. First, here are the previous results from our batch inference application. So how does AnyScale perform here? Well, quite well. If you take the same Ray pipeline without any code changes, and you run it on top of AnyScale, you can get a further reduction in AWS cost of 28%. And here is another example. As you heard earlier in the day, one of the most important LLM workload is serving. And one of the most important metrics here is how long it takes to start up a serving instance. And with AnyScale, we reduce the time to start an instance for serving the largest Llama 2 model by 14 times. This big reduction also helps us to reduce the cost by using spot instances. How is this working? Well, assume that you use an AWS spot instance. As you know, spot instances are cheap, but can be preempted. However, before they are preempted, you get a 2-minute notification. AnyScale can use this notification to start a new instance and redirect the request from the old instance to the new instance before the old instance is preempted. And by doing so, you can use spot instances with no impact whatsoever on availability. And in the process, you can save up to 3 times the cost. Okay. When we created Ray and then AnyScale, we were inspired by this famous quote from Alan Kay, the inventor of object-oriented programming and Turing Award winner. Simple things should be simple, and complex things should be possible. With AnyScale endpoints, we make simple things simple. You can literally start in minutes to build your simple application. However, the AnyScale platform exposes the full power of Ray and lets you build any kind of application, no matter how complicated it is. So really, there are no limits to what you can build with the AnyScale platform. To hear more about the AnyScale platform, please join me in welcoming Sinay Rapsat, the head of product management at AnyScale.
Thank you. All right. Well, it's actually warmer out here than it is back there. This is great. I was wondering whether I should put my sweater on. Look, it's really exciting to see all the great capabilities we've delivered on the Ray side of things to help AI innovators really build, extend, and ultimately future-proof their AI platforms. But there's a couple of other types of organizations that we also want to be able to support here. We're seeing 2 patterns emerge with organizations. We're seeing one set of organizations that are moving very, very quickly. They're starting to experiment, validate those experiments, and ultimately start to ramp up their applications, leveraging public services like what you've heard we deliver, the Anyscale Endpoints. But there's a number of other organizations that do start there, but they have more requirements. They need to find solutions that have the right privacy, the right performance, to be able to operate in the environments and at the scale that they're going to require for their applications as well. And so a big part of what we're focused on here at AnyScale is delivering a solution that helps organizations meet the needs they have today for AI applications, as well as prepare them for what they'll need tomorrow to run their innovation. And so I want to talk through the product portfolio that we have here at AnyScale. So first, we have AnyScale Endpoints. As you saw, that's our serverless solution, API-based, to give folks access to the best OSS LLMs for the best cost. And here I want to talk a little bit about what that really means. When we say the best cost, we're serious. We're now delivering large models, so Llama 70B and Code Llama 34B, for $1 per million tokens. But as we mentioned earlier, smaller models often cost less. So Llama 13B, we're now offering it for 25 cents per million tokens. And we're offering Llama 7B for 15 cents per million tokens. I'd encourage folks to take a look at this URL, go there. By the time, maybe there's some eagle-eyed folks that have already gone there and may even have actually gotten access to an API endpoint by the time I'm finished with this slide. Definitely can be done by the time I'm done with the next slide. It's a super easy process to get started and integrate LLMs into your application. But we don't just stop there. We've also created Anyscale's private endpoints. We needed to do this because organizations want to be able to have more ability to control, customize, and ultimately get the privacy that they need to get the benefit of LLM applications, both for their external as well as for their internal use cases. And in addition to that, we want to give folks the ability to really dial in the right cost by taking advantage of whatever discount structures you've been able to accomplish with your cloud providers, and be able to select which types of GPUs and CPUs you use to execute your AI workloads. We also allow folks to dial in the right level of quality by adjusting the settings that you want for the LLMs that you want to deliver in your applications. And these two solutions are built on top of the rich capabilities that are offered by the full AnyScale AI platform. And so we're gradually revealing more and more capabilities to organizations as they go along this journey and as they go along through our product portfolio. And so the AnyScale AI platform gives you the ability to operate across multiple clouds, scale your workloads automatically, and leverage the best compute that's available to run your workloads at any time, up to and including spot instances. We can dynamically schedule workloads to take advantage of the best available resources and the best available cost. We invest heavily in optimizations of CPUs and GPUs. From the single GPU perspective, making sure we pack the GPUs with workloads so that they're being used as efficiently as possible, and scaling to be able to have workloads run across multiple GPUs to take advantage of the most complex workloads you want to be able to run. For developers, we give folks the ability to maintain a single Python native environment at any scale of workload they're trying to work with, whether from their individual laptop all the way up to cloud and global scale workloads. For those folks that are working directly with the models, we offer lots of tools to help folks train models very, very quickly, as well as with quickness oftentimes comes good cost. And make sure that you can continuously tune those models as your application evolves, so too does the quality of your model need to evolve. And finally, on top of all of that, we deliver a powerful serving infrastructure, both for dynamic real-time serving as well as for batch inference, to make sure that any application architecture you want to deliver can be delivered through the AnyScale AI platform. We also integrate out of the box with a wide range of ecosystem vendors. A big part of this is to make sure that you get access to the latest, greatest application technology to be able to power your AI applications, in addition to making sure that your AI platform is ultimately truly future-proof. And this is all based on the super solid foundation of Ray, making it easier for folks to build and deliver the AI applications they want. So what we're seeing as we talk to organizations about the patterns, the application patterns they're creating, it's not just a one LLM world. Organizations will typically start with a general purpose LLM, like a ChatGPT or GPT-3.5 Turbo or a GPT-4. And they'll use that for the general knowledge that needs to be delivered as part of the application. But more and more, we're seeing folks start to train smaller models or deploy smaller models to be able to accomplish specific tasks within a broader AI application. And what we're finding is this is a perfect opportunity for open source models and ultimately AnyScale's platform to be able to deliver these capabilities to allow folks to right-size the model, right-size the cost, get the performance you need as you start to integrate multiple models into a single application, coupled with the privacy and control that you ultimately want for your applications end to end. But don't just take my word for it. We've been busy here at AnyScale, not just building this great platform and this open source solution called Ray. We've also been building LLM applications ourselves. And a lot of our energy has been focused on how do we help folks develop AI applications. So we've actually built an AI application that will help organizations develop AI applications. And so I'd like to introduce Philip, co-founder and CTO of AnyScale, and Goku, an ML engineer here at AnyScale, to tell us more about what they've built with the team. Goku, Philip.
Awesome. Thanks, Sydney. So as Sydney just mentioned, we've been hard at work both developing and productionizing LLM applications internally over the last several months. And today, we'd love to share a few of them with you and also talk about some of the challenges we faced along the way.
So we've been building the Ray Assistant, which is a tool that helps developers answer their question about the Ray ecosystem. Every day, thousands of people come to the Ray documentation to get help. And so we are building an assistant that allows easily to hear the Ray documentation and that allows you to answer the questions.
Awesome. So to actually demo this, Philip, I have some workloads that I personally need help with, and I'd love to use this to make that happen. So I've got a lot of documents in an S3 bucket, and first step, I'd love to actually load them.
All right, so how to load all text files what is the bucket?
It's called Ray-Documents.
All right, let's see what the assistant says. So it's actually not enough for this question to just query an LLM, but you want the context of Ray in the Ray documentation. So we are retrieving the relevant documents. And then if you see, it tells us how to load these documents here. And in this case, actually, the query is fairly simple. And it's actually going to use Llama 70B to answer the question. So let's run this. All right.
Excellent. So that's a lot of documents. And besides just loading them, now I want to be able to embed them. And I just spent some time on the LangChain documentation page, and I learned how to embed a couple sentences using an embedding model from Hugging Face. But we have a lot of docs, and I'd love to learn how to embed all of them in parallel.
All right. Let's ask the assistant how to parallelize the following code example over the dataset ds. Let's copy in your example. Let's see what we get. So in this case, actually, the query is a little bit more complicated. It involves code examples. And so we're actually routing the query now to GPT-4. And it's actually doing a good job. So it's actually quite impressive that it figures out that this model needs GPUs. So it's going to set the right GPU setting here. And then it also uses Ray data and predictors and then map batches to parallelize the model. So let's try it out. And then I'm also going to show. All right, so this now runs on the document, and then it shows the answer. It takes a little bit to run, and then you see here all the embeddings for the documents. Cool, so now Goku is going to tell us what challenges we run into while developing this application.
Awesome, thanks, Philip. So this application that we just saw may feel like your canonical hello world of LM applications that we've all seen probably over the last several months. But actually developing this and productionizing it certainly came with its fair share of challenges for us. To start off, as Philip mentioned at the very beginning, we had to augment these LLMs with the relevant context. And for that, we used retrieval augmented generation, or RAG. And if we hadn't done this, our LLMs would hallucinate incorrect responses. Now, when building an application like this, there are a lot of moving pieces here. We had to load our data, chunk it, embed it, index it, and of course, put it all together to create the application itself. And we wanted our application to not just work today, but continue to work as our data sources grow and our models grow. So to help with this, we used Ray Data and Ray Serve in order to scale out all of these workloads, all within Python with minimal changes to our code. Now, when you have so many moving pieces like this, there are so many different configurations that you can have. For example, what kind of chunking logic to use, what embedding models to use, and of course, what LLMs to actually use as well. So we actually spend a lot of time thinking about evaluation because it's pretty non-trivial to compare different configurations across each other for a generative task like this. So we looked at both component-wise and overall evaluation, and we used the scale workloads from the previous step to be able to run a lot of different experiments. And with our experiments, of course, we found that the most performant model was often the most expensive and closed source model as well. But open source models like Llama 270B were right behind in terms of quality at a fraction of the cost. But our main challenge was that we wanted to serve the most performant model, but also in the most cost-effective way. So we implemented a hybrid LLM routing approach where we basically trained a small classifier that can discern which LLM a specific query should go to. And for our specific application, we found that over 95% of queries can be sent to an open source model like Llama 270B, but a small subset of highly complex queries can be routed to a more expensive and larger model. This was our way of bridging the gap between closed source and open source models, but most importantly, helping us serve the best application we could to all of you. Now, putting all of this together, the AnyScale platform was beyond crucial. When it came to development, we got to choose the exact environment and compute needs that we wanted to have on top of our workspaces. And then taking all this development and actually putting it into production, we could use that exact same configuration to now do things like running jobs, like indexing and embedding new data that's coming in, or of course, serving our actual application in a highly scalable and available manner. Now, creating an application like this and many others has already had tremendous impact on both our products and our productivity, but it's also opened up a whole new class of algorithms that just previously weren't possible for us. So to talk a little bit more about this, I'd like to invite Sydney back up on stage. Thank you.
Good stuff. Good stuff, folks. So as you've seen, we've developed a really cool application to help folks build AI applications. And along the way, we learned a lot. Go could call them challenges. I also might call them learnings. One of the things that we learned was the importance of debugging. And so another AI application that the team created, that one gentleman is going to get to take you through, is about helping folks debug AI applications. So please join me in welcoming Sofiane, ML engineer here at AnyScale.
Well, thank you, Sydney. So as you can imagine, working on AI infrastructure, we actually have to go through a lot of debugging and troubleshooting. So let me start with a very simple example here. And it's going to be too simple. All what I have is one Jupyter Notebook cell that is trying to import the request module. And if I were to run it, surprise, surprise, it's going to fail. It's a debugging demo. So notice how the Anyscale doctor icon has showed up right here. It's basically recognized that something went wrong and it's offering to help. But I know what you're thinking. You're thinking this is a module not found error. It's one of the most common errors that we have to deal with as developers. And the fix is actually quite simple. You just need to start a terminal, activate the right conda environment if you're using one, and then get the name of the module if you don't know it. And then depending on the packaging system, perhaps you're using pib or poetry, you need to type that command. So it's a simple fix, but it's actually one that requires understanding the context, understanding the environment that you're running in. And that's perhaps why the majority of us have developed that muscle memory to run those type of commands manually. So let's take a look at what the Anyscale doctor has done here. So first, it categorized the problem as a dependency issue. And then it decided to consult CodeLlama for help. And now it's offering me a quick fix right inside my environment. So if I were to click on it, it's going to start a terminal, it's going to issue the pip install command, and when it's over, I can run it again, and it passes. Thank you. This is a simple problem. Let's move on to something that is slightly more complex. And what I have here is a logic that is trying to embed a large number of documents into a vector database. And it also has failed, resulting in this really massive log. So I'm going to ask the Anyscale doctor again for help here. And usually my own process towards trying to debug those type of applications is I'm not the most patient person, so I'll just scroll through the log as fast as I can until I find something that looks suspicious. And then if I'm lucky with a little bit of research, I would come up with a theory and come back and fix it and be out of it in 10 or 15 minutes. But it's not uncommon that sometimes I need to collect more information. Perhaps I need to look at the Ray dashboard and get more logs, or I need to look at the system metrics through the Grafana dashboard. If it's a really bad day, I might find myself digging through GitHub trying to find that issue, or even worse, write it myself. We dread those type of issues as developers because we know they can be massive productivity hits. I'm sure a lot of us here have been in a place where a task that should have taken minutes, it takes hours or perhaps days. So let's take a look here and see what the Anyscale doctor has done. So first, it started by summarizing the problem. So unlike the first example, where the entire log was simply the error, in this case, we have a log of thousands of lines, and finding the relevant parts is crucial. And then it went in to classify this problem as an infrastructure issue. And then it decided to consult the Ray Assistant for help. The Ray Assistant, the very same system that Philip and Goko just presented. Except what Philip showed you is that system powering the UI of the Ray documentation. And in this case, we're actually using it to power a branch of the Anyscale Doctor. And it's again providing me an error right in my environment. So if I were to hover over this error and look through it, obviously don't need to read this, you would find an error message that is very personalized. It's basically telling me that the logic that I'm trying to run here requires access to precisely 2 GPUs. And my environment consists of CPUs only. And it's not stopping here. It's going on to explain in more details ways that I can fix this problem. It's suggesting that maybe I need to update my cluster to include access to the required hardware. Perhaps refactor my logic so I can run it on CPU. Both are examples of things that I actually want to consider. So we've seen the Anyscale Doctor helping with small repetitive tasks that until shortly were outside the capabilities of the current tooling, and with complex tasks that requires understanding the environment, that requires the ability to summarize and research. So let's switch back to the slides and talk a little bit about how we build the Anyscale Doctor. So we needed to start with data as the foundation. We had to go and categorize a large number of errors to understand what type of issues our customers are seeing. And when it came the time to build the LLM application, it wasn't just a single application. It was a graph of LLM nodes where we had to break down the tasks into smaller parts where we can optimize and choose the best LLM for the task. And that's perhaps our biggest takeaway out of this project. It's very hard to do those type of applications and deliver the experiences we wanted to deliver with a single-shot LLM. We obviously needed a RAG application. We needed to overcome that knowledge gap of LLMs, and for that, we used the Ray Assistant. And finally, all of this required a reliable serving infrastructure, and for that, we used the Anyscale Endpoints. This is a simplified version of the architecture of the Anyscale Doctor, and you can see a mixture of models being used here, all the way from Llama 70B to Code Llama to the Ray Assistant as well. And all of this is made possible by the power of the AnyScale Platform, from development to production, as well as the AnyScale Endpoint and the Ray ecosystem. So we're excited for you to build amazing applications on the AnyScale Platform, and hopefully the AnyScale Doctor can help you do that just a little bit faster. With that, I'd like to invite Jan back into the stage, and thank you very much.
Thank you, Sofian. So during this keynote, you have seen how you can use Ray and Anyscale for developing, scaling, and productizing all your LLM applications, from the simplest one to the most complex one. There is really no limit to what you can do with Ray and Anyscale. And now, there is a time for the last act of the keynote. Everyone here knows and loves NVIDIA. They have been building the chips that have powered the LLM revolution. So please join me in welcoming Justin Boitano, the VP of NVIDIA's AI Enterprise, who is going to share with us some exciting news about Ray and NVIDIA's AI ecosystem.
Hey, okay. Excellent. Look at this. A packed house. I just want to start by congratulating the Ray ecosystem and the Anyscale team. They've done an amazing job building this community. And that's the reason that we're here from NVIDIA, is we've been watching from the outside. We're an accelerated computing company, but Ray is really this foundational runtime that the world needs to scale LLMs across the data center extremely efficiently. And the AnyScale Platform and Ray provide that to customers. They make it super easy to go to thousands of nodes And it makes it really seamless for customers to take large language models and scale them into production. As you know, NVIDIA is an accelerated computing company. And this means we try to squeeze the performance out of every open framework. We usually work with frameworks like TensorFlow and PyTorch. We pull them down on a monthly basis to keep up with API progress in the ecosystem. We fully tune them to run on our GPUs, on CPUs, and on networking to give customers the benefits and advantage of performance increases and cost savings. And we upstream all that work back into the community. About 5 years ago, we also realized that accelerated computing really needed to come to the world of data science. And so we built on top of Apache Arrow, a project that we maintain that's called Rapids. And it brings accelerated computing into the world of scikit-learn and pandas. And again, it's an open project for the community. And the reason that we're here is we see the importance of bringing together the world's best accelerated computing together with the world's best distributed computing. And we see this partnership with Ray and Anyscale being just a very symbiotic and natural partnership. The beauty of the open source is that innovation can happen really quickly. Last week, we announced a new project we call TensorRT LLM, and it's already been included into Ray Serve. And the value of this is immense. You know, customers, if they benchmark TensorRT LLM running on our Hopper H100 GPUs versus our previous generation GPUs, see this dramatic 8x performance improvement. They see a 5x reduction in the cost to run large language models, and they get a 5x improvement in terms of energy efficiency in running large language models at scale, which is really important for, you know, the industry as a whole. But beyond TensorRT LLM, there's a number of other projects, such as NeMo, which is our large language model framework. It's an open cloud-native framework that helps with everything from training models to tuning models, running them efficiently in production, and guardrailing them so that they stay on topic. And the work that we're doing through TensorRT LLM and NeMo will be, you know, first-class citizens and fully integrated into the Ray ecosystem, which is great for the community. But the question I always get from customers is, okay, you know, how do we take generative AI from this research phase into production? And as I walk into enterprises around the world, what I constantly hear from them is they've got, you know, dozens of these projects underway. They're trying to use generative AI to deliver better co-pilots for developers to write code faster and be more productive. They're trying to provide natural language interfaces into IT and HR systems. They're trying to provide customer support chatbots that help customers solve their problems on their own. And so the use cases are broad and wide, but the question is, like, how do we deliver this value in a way that customers can run these in production? Now, NVIDIA knows working in open source is fantastic for unlocking innovation quickly, but you need a downstream. NVIDIA's downstream of our AI software is called NVIDIA AI Enterprise. And this is really the operating system of artificial intelligence. And I say this because, you know, we work to do all this security scanning and patching and maintenance and maintain API stability for people that want to run these large language models in production, which is critical for enterprises who don't have the manpower to roll their own distribution and run it in production. So as part of the work that we're doing with the Anyscale team is we're going to certify NVIDIA AI Enterprise to run on AnyScale Platform. So customers, if they want to run these large language models in production, can have the combined support from Anyscale and NVIDIA and have the confidence that they can run large language models in production. So it's just what the industry needs kind of at this, the beginning here of you know, making large language models broadly available to the world's enterprises. So thank you very much. Appreciate you guys having me.
Thank you, Justin. And thank you all for a great start of our Ray Summit. This brings us to the lunch break, but a few announcements before then. First, please visit the Ray ground. And before that, if you haven't gotten your badge, please do so, because you are going to need it for the Ray ground and for the breakout sessions. Also, tomorrow Keynote is going to start at 9 a.m. With that, thank you again, and enjoy the rest of the day.